So I'm going to talk about the Lightning Network overview, or how I view and how I dissect the different layers of the network. I like my presentations to be interactive, so whenever something jumps at you, please raise your hand or just shout at me. Also because I don't have 45 minutes as I planned, so please help me fill those 45 minutes. I usually distinguish these different layers in Lightning, and the first question that I usually get is, wait, I thought this is layer 2. What are these then? And that's also why one of the reasons why I usually talk about off-chain protocols, because you can stack these in arbitrary orders and do fun stuff. But this is the Lightning stack as we have it currently in the build specification. We have a transport layer, which is basically just the encryption layer on the raw TCP connection. We have a framing and feature negotiation in the base layer. That is basically how our messages are formatted and how do we negotiate which features we support. And then we have an update layer, which basically just goes up to here. And this is an old slide. I should have updated that because there's now 3 proposals. There's the LN penalty mechanism, which is in the bolts. This duplex micropayment channels, it's the really old paper that nobody really cares about anymore, but I wrote it, so I usually put it in there. And there's supposed to be the L2 update mechanism as well. And then I'll get back to gossip later. Then we have the transfer layer, which is basically how do we negotiate incremental payments over an individual channel. And we have the multi-hop layer, which is the Sphinx layer, which allows us to then extend this relationship over multiple hops in the network. And the last layer we have is the gossip layer, which is sort of part in the update layer, but it's not really. It's really orthogonal to the rest of the negotiation part, but it's really useful for us to. It's also transported in base layer, but we use it for updating of our routing table and how we update your view of the topology. And basically what you should take away from this is you can switch these up however you want. We could drop the Sphinx layer and the HLC layer and just negotiate between the 2 participants in a channel and say, hey, here you go, another $1, or here you go, another Satoshi, and just not care about any of this. And on the other hand, we could replace all of this with a completely different layer. So we could use TLS here and have an SMTP server here. So that's one thing that I actually wanted to do at some point, was basically have Lightning over SMTP, because why not? And everybody understands mail, right? So, and you can mix and match these. And the reason why we have multiple here is because we can even swap out individual parts quite easily without interfering too much with the other layers. That's not all that true in LN penalty, because that bleeds into the upper layers, as we will see later. But for the most part, all of these are distinct, and you can swap them out with something new or something that better suits your use case. Okay. So let's start with the actual layering, or the actual layers. As I mentioned, we have on the bottom, the bottommost layer is the transport layer. And our goals here, while creating a specification, were basically to authenticate the node identity. So we're actually talking to the node we are expecting to talk to. We want to be fingerprint resistant. So if I contact a node in the network without knowing its ID, it should be hard for me to guess who it is. And we want to set up the transport encryption for the usual trio of confidentiality, authentication, and integrity for all of our messages. And the way we do that is this interesting noise protocol framework, which is basically a set of tools that you can rearrange however you want. And if you follow the construction of the noise protocol, of which we chose the XK variant, you can have this. So we chose the SHA-256 hashing algorithm. We have a ChaCha20 algorithm for the encryption. This basically just creates a long stream of pseudo-random data that we can then XOR with the actual messages that we're transferring. And we have poly 1305 for the message authentication codes. One thing that is really important, and I'm sure you're all aware of this, but your node IDs are actually persistent. So whenever you start up, you basically generate some secret, and from that secret you generate the public key. That is going to be your node's identity for the remainder of the lifetime of that node. This is very different from Bitcoin, where we try as much as we can not to have a persistent identity, because we don't need that in Bitcoin itself. So nodes in Bitcoin itself do not have an identity, and we try our hardest to make it hard for people to actually learn or be able to distinguish two different nodes, or be able to say, okay, this is the node I saw like a month ago.
What was the rationale to using the persistent identities? Just
so the persistent identities will become important once we start routing payments, because we need to have a way to address individual nodes in the network. We can. So what we can do is have single nodes have multiple identities, but they will then not be able to sort of merge. You would have to create virtual channels between them to actually show, hey, you can go if I have 3 channels here and 3 channels here, and you have to run them on different identities, then you can't really bridge them, or you have no way of telling people, hey, by the way, you can also pretend that we are connected as well. Okay. It's just useful for addressability, and that's how we locate people in the network that we are trying to pay. Since we don't have addresses like we have in Bitcoin, we needed to go that way.
I was just thinking about this idea of virtual identities with sort of these virtual channels. Is that a way somebody can try to collect more fees? Putting themselves behind a virtual identity?
Absolutely. I mean, you can basically create a subnetwork that you yourself control fully, and then pretend it's really expensive to route through. But if you have that opportunity, you could do the same without going through the lengths of pretending to be multiple identities. So if you have sort of a monopoly on a certain part of the network, which would be required for this virtual network to be workable, then you could just be a single node and just have really expensive edges going out. Right, yeah. And the one thing that you could do if you pretend to be multiple nodes is to make it hard for people to locate you and route around you. But the hope is that would automatically happen at some point, and people would see, okay, there's a lot of traffic going through this region of the network. I could just short circuit it and make a bit of money and basically sit right next to this expensive part and grab a bit of those fees as well. So the Diffie-Hellman part comes to play when you do the authentication of the node, and to establish the secret. So what you do is basically you contact the node, you initiate a Diffie-Hellman protocol, and if you both reach the same shared secret at the end, you're sure that the other side was actually who you were talking about.
And that's not considered part of the noise protocol?
It is part of the noise protocol.
Okay.
So that, yeah.
It's also one of the reasons why we need persistent identities, because
Yes.
noise XK wouldn't work without persistent identities.
Exactly. So
it's known, right?
It's because we need to authenticate a node, and then everything cascades from there, basically.
So maybe just adding the XK means that X is the sender or the one who initiates the connection, and K is the person you connect to, and K means it's the known identity, so you know the public key, otherwise it doesn't work, right?
Is that the reason for that XK?
I think so.
Okay, cool.
So X stands for it's unknown, and K stands for known, and there's a third letter which I forgot because we don't use it.
Okay.
Can you repeat that? So X is
So if you look at the noise protocol framework, right? You have basically these noise protocols, and then they always have two letters. And the first letter always stands for the person who initiates something, and the second letter always stands for somebody who is the receiver. And the X means basically that the identity is not known, and K is known means the identity is known, right? Which means that if I want to peer to you, I know your public key, your persistent identity, and then I can initiate the key exchange for Diffie-Hellman and all of that.
Yeah.
Okay, thank you.
Yeah, the naming scheme is a bit weird. Also we copied the exact nomenclature in the bold, which makes all of this feel really dissonant to the rest of the bolds, but it's very clear. So maybe we should adapt the rest of the bolds. So going one layer up, we actually have the message framing. Since we now have an encrypted stream of bytes going back and forth, we need to have some way of saying, okay, how do we send individual messages? And messages are just a blob of data that has a certain length, right? So what we do is we have a 2-byte encrypted message length. 2-byte, that means that all of our messages are limited to 65K. Followed by a 16-byte MAC of the encrypted message length. MAC in this case is just an HMAC using SHA-256. We have an encrypted lightning message, which is the actual payload, and followed by a 16-byte MAC of the lightning message, and that's again a SHA-256 based HMAC. Anybody see anything weird about this?
Why do you MAC before encrypting and after encrypting? Like, I see 3 different MACs. One of them isn't here. One of them is part of the noise protocol itself. The poly there. Then you have here MAC of the encrypted and another MAC of the unencrypted.
Yes.
If I understand correctly.
So yes, we actually do have. So the poly 1305 is used for the setup, not for the actual transfer anymore. So the weird part is that this 16-byte HMAC covers 2 bytes here. It's a huge waste. Any idea why we are doing that?
The onion, does it have to do with the onion route?
Mm-hmm. This is only single hop here. The two of us are exchanging messages, and I'm saying to you, hey, the next 4 bytes are a message, and here are 16 bytes of HMAC that I just told you that 4 bytes will be the message.
Maybe you would want to decrypt the length before, so you can then know how long the message you're receiving. And if you want to decrypt something, you need a MAC for it to be authenticated. But why would you want to decrypt the length before the message? That's what.
So the one of the reasons is that it's common practice to check an HMAC before decrypting. So, and if we had only this last HMAC here, we would actually have to decrypt this, read the message to find this HMAC here. So due to the way that we construct these, we first need to read these 2 bytes. To read these first 2 bytes, we need to check the HMAC, and so that's the main reason why we have these. What could happen if somebody were to tamper with our 2-byte length here?
You won't find the HMAC.
Exactly. So we wouldn't find the HMAC. We would fail the message. And what an attacker could basically do is, by flipping individual bits here, he could attempt to figure out what the message length is, right? If I flip a bit here and the connection hangs afterwards, then I can be sure that, okay, I flipped a bit that was sort of longer than the actual message, and it was waiting for me for the remainder of the message after 10 bytes. So this must be longer than 10 bytes. If on the other hand the door is slammed shut in my face, that means that I flipped a bit that was so the message was shorter than the bit I flipped. So that way you can actually probe for message length and basically decrypt this in a roundabout way.
I still understand why do you need a 16-byte HMAC?
So the 16-byte HMAC is basically just because that's a 128 bits of security. Yeah.
So you're not using some kind of increasing nonce to avoid this kind of attack? By repeating to avoid probing?
So what we do is we every, I think it's 500 messages, we switch the encryption keys here, but that's for successful messages.
That's for forward secrecy.
Yes, but no, we don't have any nonce in here that would disallow that. Also because when this fails, the connection gets dropped, and we reinitiate a new connection, and so that counter doesn't get increased. Okay. Cool. And the second part of the second layer is basically control messages. How do we communicate over this channel? And once we have our framing mechanism, how do we actually negotiate what features we support? What's the protocol format going forward? So the first message we actually send is an init message, and each message is prefixed again by a 2-byte type. So that's type 16 here, and this is basically just a two variable length field message called global features and local features. The way we describe these is basically by having the saying, okay, 2 bytes of gflen, and then gflen bytes of global features. It's basically just a variable length field in this case. And these are bit fields with individual bits set depending on which features you enable or disable. So unlike other protocols, we have agreed upon set of feature bits that we can enable or disable. And one peculiarity we have in here is that depending on the position of the bit, it's either a required feature or it's a nice optional feature that you have. So we usually give these assign these feature bits in pairs. One is even and one is odd, and the saying is it's okay to be odd. So if we assign bits 0 and 1, basically using the bit 1 means, hey, I'd like to use this feature, but it's okay if you don't support it yet. And the 0 bit, being the even bit, means, hey, I'd like to use this feature, and if you don't, we can't go on, right? So if we were to, at some point, introduce a new serialization format for our messages, then that would likely be, on one side, it would be, okay, I do understand this this new feature. Basically, let's switch protocol. And on the other side, it would be, okay, I require you to know this protocol. Otherwise, we can't continue talking anymore. And there's been a bit of controversy whether it's the numeric value that is expressed by the bit or whether it's a position of the bit. It's a position of the bit. So if we have bit 4, for example, that's 16 expressed numerically, and that's not what you should be looking at, but it's the 4th bit and it's even. Because and finally we have error messages, which are basically just, here's some random error, I don't know what you're doing. The interesting part is that we have data associated with this. This usually ends up being just an ASCII string, basically telling you done fucked up, because we try to give very little information. Otherwise, we'd be spilling internals from our implementation. And the other part is that we actually associate errors with a channel if this channel exists. So if we had some negotiation on a channel that went wrong, I'm going to tell you, hey, by the way, this is the channel that you did something wrong, and if it's a lower layer error that is not associated with a specific channel. This is simply set to all zeros. That's basically it. The error itself does not really say whether it's fatal or not. We just close the connection if it is. It usually is. Okay. The next layer up is basically the update layer, and you might have seen this slide before, but I'm lazy and I didn't redraw it. So the update layer is basically the core part of the whole Lightning protocol stack, and its whole use is basically for us to make sure that that we can lock some funds on chain, then go somewhere else, do our negotiations, and then come back and reflect those, or reflect the aggregate of our off-chain decisions back onto the blockchain. So what we do is, if we have two participants, Alice and Bob, that meet somewhere, we have the blockchain, which has Alice has 5 Bitcoin, Bob has 5 Bitcoins, and Carol has 5 Bitcoins. We then go ahead and lock in part of the state by basically transferring these funds onto multisig. And we then go somewhere else and start negotiating among ourselves on what happens with these funds. So importantly here is that the initial state always reflects the state that we locked in on the blockchain. So this is basically our off-chain contract that says, okay, Alice gets 5 and Bob gets 5. And then we can start updating these and actually transferring back and forth. And what I usually, and the important part here is that we're not just discussing who gets what part of this, but we can create arbitrary structures on top of this. So in this case, what I showed here so far is always these contracts always create 2 outputs as their end result. One going to Alice and one going to Bob, but we could do whatever we want on top of this. Basically, we are negotiating how we will eventually create outputs. What happens to these outputs, we can then decide later. So we could create other off-chain contracts on top of this by basically just stacking them. And the whole complexity of these. Let me go ahead. And then eventually we take this latest state and go back to the blockchain and apply the aggregate of these negotiations. We apply them back to our blockchain, and in this case we have 6 and 4 as final state. So we update the on-chain state here. And actually, the whole complexity in all of this comes from the fact that if this is our latest state that we agreed upon, I need to make sure that, for example, in this case, Bob has 9. So Bob would definitely prefer this state over this one where he only has 4, right? So the update layer's central use is basically to invalidate all of the prior states once we have agreed on a new one. And that's the whole magic of all of these off-chain protocols. That's it. Goodbye. Okay, so these update protocols are we've gone through in a number of iterations. We had the simple micropayment channels, we had the duplex micropayment channels, we had the Lightning protocol, and now we have L2. Everybody take a drink because I mentioned L2. And as I showed before, we can actually swap them out quite easily. Well, if they actually bring us more features than we had so far. But we will have a lecture on that later on as well. Okay. One layer up is the transfer layer, and that's specified in bolt 2. And that basically is a construction where we create, on top of the update layer, we create an output that has a very specific structure, namely that that either I show a secret and I can then grab my money, or I don't show a secret and it eventually times out, right? So the I can actually show you the output first. Come on. Okay. So this is the output script we have in HLCs. This is Lightning Network penalty specific because of. Wait a second. Where is the revocation secret? There it is. So so this is one of the parts where I mentioned that some of these layers might bleed into one another. Because in the Lightning penalty mechanism, these HLCs might actually end up on the blockchain itself. We need to make sure that we could also revoke these. So that's why we have this initial step here. But from the op-if downwards is basically what the generic HLC would look like. We have we have two possible outcomes here. We have the success and the timeout case. In the success case, we basically it's me extending a promise to somebody, to my counterparty, and saying, hey, if you can provide me with a secret that hashes to A, then you can get this money. And in a collaborative success, the receiving part endpoint basically shows, hey, here's my preimage to your hash, and we both agree that, well, we just remove that, increase the balance of the recipient, and decrease the balance of the sender. Then we have the uncollaborative case, where we basically say, okay, this thing is about to time out. So I showed you the secret, but you still don't want to give me my funds. So I will go. I will take this whole contract, drop it onto the blockchain, make sure that this HTLC output actually is created on the blockchain itself, and then on the blockchain, before the timeout expires, I can create a transaction that spends those funds towards my wallet.
So what's the difference between the second and last case? So just
between this case and this case?
Yeah. So it's the last is timeout.
So in this case, the recipient actually has the secret and can therefore claim the money. In this case, the recipient does not have the money and does not have the secret, and therefore it drops to the blockchain, and we just wait for the timeout to expire, at which point the sender can claim back the money. So in this case, the recipient gets the money. In this case, the sender gets the money back. So this is success, and this is timeout case. Yes?
Isn't the timeout the fact that you didn't succeed to collaborate to get fail the HTLC?
How do you mean?
I mean, in the case of timeouts, you get an awful lot of HTLC outputs between Alice and Bob, and Bob at some point should update fail the HTLC rights.
Only so there he cannot always fail the HTLC, right? For example, if Alice extends an offer to Bob, and then Bob goes ahead and extend that offer to Charlie, these two HTLCs are now bound together.
Yeah, and Bob is not going to revocate to fail the background one.
Exactly. Because Charlie still has a chance to actually have the pre-image and then sort of.
Yeah, so it's more fail on the whole collaboration chain.
Yes. So in most cases, so this should be really rare. This should be rare. This is our preferred outcome because it does not involve going from off-chain to on-chain. But we need to be prepared if that ever happens. And yes, these are actually dropping to chain. Yes.
I'm like two questions basically. Like first of all, I don't understand why it's titled off-chain case, because I mean the bottom two parts we are going to the chain.
So in this case, we start off-chain, and then we end up on-chain in these cases. And in this case, we stay off-chain.
And wouldn't we also then name their like collaborative failure, where like
yes. So there is a third case where where we say fourth case where we say, okay, this is a collaborative failure, but that does not have any on-chain reflection, basically. So this is basically I'm trying to show the cases where you start with an HLC and then how you resolve them. And in the off-chain, in the collaborative failure case, you'd basically just agree, okay, I have no idea on how to, I as a recipient have no idea on how to resolve this. Please go ahead, you get your money back. But that doesn't have really an on-chain equivalent other than the timeout, basically. Yes?
I never fully understood.
So this is the on-chain case, by the way.
I never understood so we have a second stage transaction for the HLC timeout and success.
Mm-hmm.
And for timeout, I can understand because we want to couple the CSV from the absolute timeout.
So for the timeout case, we actually need to move these funds. We need to move these. So we have the HLC on-chain. We now have the timeout expired. And now we need to move them in order for us to be sure that the recipient side might not jump at us and then say, hey, I have the pre-image after all, please give me my money. So you move the funds out of the reach from the recipient by having this sweep transaction. If you weren't doing that, that would be bad. Also, in the uncollaborative success case, you need to move the funds away, because let's say we have 14 blocks as timeouts, and now 10 of them have passed, and I suddenly got the pre-image. Then I need to pull the funds quickly. Otherwise, my counterparty suddenly has the timeout expire and can then also pull the funds. And then we are in a race condition, which we try to avoid at all costs.
I guess my question was like, why can't the HLC success transaction just be the HLC output? Does it need a second transaction? Like I get like for HLC timeout, we need a second stage. But I was never 100% clear to me why that was necessary for the success case.
So for the success case, it's basically the case I just mentioned, right? Let me be the sender and you be the recipient. We have a timeout of 10 blocks, we drop on chain because of some reason, and you have the pre-image, right? But you let the HLC sit there. So I will wait for 10 blocks to expire and then try to pull the funds away from you, because the timeout has now expired. I can pull back my funds, despite you having the pre-image, right? So you need to make sure that you pull the funds away from that shared output before I get the ability to pull it towards me.
Okay, maybe I should write this down later. Like whether I have the pre-image or actual signed HLC success transaction. Yeah. Maybe I'll ask offline.
Oh, okay, yeah.
You may have a grace period after the expiration of timeout to let the recipient provide the pre-image between the few blocks following the time expiration.
That is of course true. I mean, I could be benevolent and just say, okay, I'm not going to touch this for 10 minutes or 3 days, and still allow you to grab those funds. That works if you don't have any downstream or upstream effects.
You may have downstream, but the grace period must be less than the timeout buffer between each node.
Yes. So if we have this waterfall kind of structure,
it's a bit touchy, but that works.
I mean, I can always give you more time. The important part is that I have the secret in time to pull from upstream. I don't care that much about downstream because, well, that's somebody else's problem. But what I care is that if you are able to pull funds from me, I should also be able to pull from upstream. So we try to make these timeout deltas as small as possible, because, well, worst case, these actually sum up over the length of the route. So if the
these Unix timeouts or are these like block timeouts?
They're all expressed in blocks, because blocks are timestamps. Very granular, by the way. So we this tendency to have minimal CLTV deltas, because they accumulate over multiple hops, leads us to not give too much slack to our downstream nodes when it comes to providing us with a secret.
It's a trade-off between locking funds in the HTLC chain and giving freedom to the final recipient.
So the so I see your desire to make payments actually work on this, but this is already the case where we are in a really bad situation, because this means that we have been waiting for hours or days for this payment to settle, and hopefully we.
I mean, not necessarily a huge buffer, but 2 or 3 blocks. That's.
Yeah, no. I get what you're trying to do, but it's just.
But it has to be always smaller for every hop, no?
Yeah, that's why they accumulate along the path of a payment, is because we need so if I promise to Charlie something, that promise needs to expire before my upstream offer from Alice expires, because I still need to have time to turn around and say, hey, this happened, give me my money.
Is there a good number used for the delta between every hop?
That totally depends on your own preference and what you feel comfortable with. Basically, doing this turnaround movement.
You being the sender or the routing nodes in between.
The routing node in between. So I need to have. I basically have a certain uptime profile. So I check in once every hour or so, or I'm up 24/7. And then I know that based on the current congestion on the network, I can get my transaction confirmed in X blocks. Then I need to basically make sure that I check in time, and that I have enough time to basically take this and turn around and claim the downstream, the upstream payment in time using an on-chain transaction. So there's this trade-off between long CLTV deltas but low on-chain fees, or really having tiny CLTV deltas but being happy to overpay like the fee rate by.
In practice, do you see nodes like gravitating towards like some range of number, or they kind of all over the place?
So at some point, LND started offering 144 blocks as CLTV delta, which is huge.
144.
It's a day.
A day.
And Sea Lightning started off with 6 blocks, which is an hour, and we've sort of seen this. We've since started going a bit higher, and I think LND is considering going a bit lower at some point.
We're at 40.
What?
40.
For a CLTV delta?
Yeah.
Oh, okay.
We moved to 40.
That's better.
That's a big range from 6 blocks to 144 and 40 in between. So
Yeah.
And
So,
if you unlock, you can have 6 blocks in 20 minutes. Right? Block variance is very, very rare.
well, 6 blocks in 20 minutes, that's quite
It's not impossible.
quite a deviation from the
It
mean,
is,
but
of course, but we're talking about like extreme cases. Right?
yeah. So if you had a full day of CLTV delta, and you had a 6-hop route, which is sort of the norm, then you'd be waiting 6 days for your funds to actually come back, which is sort of the opposite of what we're trying to do, immediate payments and stuff. Maybe not the best trade-off.
Is there any implementation charging fee based on the data logs?
So you can, since it's you as an operator determining both the CLTV delta as well as the fee levels, you can put whatever thing you want in there.
LND will adjust the cost and pathfinding based on the time lock. So LND will introduce like an artificial cost of the time value of money.
Yeah,
Yeah.
that makes sense.
We have scores in C Lightning as well that try to consider different options. Basically, we take all of these signals, being fees, being CLTV deltas, and prior experience, and we'll combine them into a single score for a channel. And that score will be used for route selection as well.
That's something coming in the future.
No, that's implemented right now. But that's on the route finding part, not on the me as a routing node. I determine what my levels would be. Yes, it would be basically you as an operator deciding what you feel comfortable with.
It's interesting that you mentioned time value of money. Does that mean that you see this delta change as maybe the price go up, or because people want to go on chain and sell their coins? I don't know.
I think it's more of an annoyance because in the worst case, you could have your funds locked up for days and days.
Yeah. So our hope is that we never get to these cases, and even less these cases. So I was saying that we have the off-chain case, and this is basically identical. We just, in this case, we need to drop to chain. In this case, we are already on chain. So all of these protocols are always replayable on the blockchain itself. And us basically taking the negotiation off the blockchain and having an off-chain protocol is sort of an optimization, basically. Yeah, collaborative success in this case doesn't make any sense because, well, we're on chain anyway, so why even try to resolve that? Okay, I've shown you this slide. One layer up, we get to the Sphinx layer, which is why do I have multiple? Oh, okay, yeah. So this is finally the Sphinx layer. This is the topmost layer, and this is how we communicate how to get from the sender to the recipient without telling the intermediate nodes what happens. So we will have loads of these tomorrow afternoon, but this is sort of the simple case, and I'll quickly step through. Who here knows how onion routing works? Perfect. I could have skipped that slide. Okay. So this is the routing packet. It's completely obfuscated. You can't really see anything. We're currently at node A. Node A has just received all of this blob. Now, through some magic called ECDH, A is able to generate a shared secret with the original creator of this package. Using the shared secret, it can decrypt the entire onion. So it will take the entire blob. It will generate using the shared secret will generate a cha-cha-20 random stream. It will XOR all of this, and it will decrypt this whole thing, stripping one layer of the onion. The payload for A is basically saying you should forward this to B. So what A then does is it drops the part that was destined for it, because that's of no use to B anymore. B will get this encrypted blob here, and through the same magic that we've seen before, it will generate a shared secret, and it will also decrypt, get to see that it's supposed to forward to C, strip his part, forward this to C, and so on and so forth.
It's a part that's rotated to the back, right? I forget. To keep the block consistent in size or something.
Yes, we will. I'll talk in length about that tomorrow. That's actually the only difficult part in the whole protocol. So I will have lots of fun talking about that.
Is there a different mark like a different 2 marks at every layer?
So this is also macked, yes.
With 2 different marks, one for length and one for.
No, this is actually constant length, due to what James will be saying. So the entire onion packet that we create and attach to every HLC is actually one version byte, plus 33 bytes ephemeral key, which is what we use for the ECDH computation. And we have 1,300 bytes of blob. And then we have a 32-byte trailing HMAC. And the HMAC is over the entirety of the blob, basically. And since that's constant size, we don't need to have that. Also, the length could be inferred by the package that we are using to transfer this. So we have the base communication layer that gives us a length, and then we have the message, which is update add HLC, which I guess Rene will be talking about later.
The base communication layer isn't authenticated.
The base communication layer is authenticated.
What's the base communication
It's a noise XK layer.
Oh, so
yeah.
Onion is on top of the noise.
Oh yes.
Okay.
Yes. So the onion is basically one field in one of the messages that we transfer over this entire stack. And the only
CPU power wasted for
this actually works out quite nicely. So basically, just to end up is E then decrypts and sees, oh, I'm the terminal node. I shouldn't do anything more. This is actually destined for me. So SHA-SHA-20 is incredibly efficient, and we can do this quite nicely. But yes, this gets quite deep in the layer stack. So yeah, this is actually one of the only parts that is cross channel, and this basically means that we receive something on one side, elaborate stuff, and then send the final part, send the final product of this onwards. The other part is of course HLCs. These are tightly bound to each other. So every HLC has one of these blobs attached. And we will also see on how to return error messages using that same mechanism, which is kind of a bit more difficult because, well, we don't have a central planner that, which is the case where we have the forward path. You're looking at me like...
Yeah, because I just lost you.
So
but that was my concentration that was missing. So
yeah, the forward path is easy because the sender actually computes the entire path. And on the backward side, we don't have this global view of where this packet is going through, so we need to make up stuff on the fly. That's the only difficulty.
Can you explain a bit on the ephemeral keys and how does that get exchanged? So you exchange the keys every time you construct a route?
I will defer to tomorrow. That's basically the whole secret behind the shared secret construction. It is AEC Diffie-Hellman that is going to use that with the node ID that we're targeting, and then that creates a shared secret that we can then use to decrypt this stuff. And the final layer that we need to talk about is the gossip layer, and I'm told somebody will cover that tomorrow or today.
I'm supposed to talk tomorrow a little bit about gossip.
Good. Then ask Rene about details. I've stopped working on the gossip layer because it got too complex.
Oh.
No, it basically is how we exchange information in the network about which channels exist and which nodes exist in the network and what their different features are, so that we as a sender can then use this view of the network topology to create a path from me to whoever my recipient is. And the extra information that we pack into the gossip messages, such as features and so on, allow us to do sort of rolling upgrades in the network, and just add new features as they come in, and basically make best use of them. There is this common misconception that you have to have a very, very good view of the Lightning Network in order for you to perform payments. Basically, you knowing any path from you to anybody to your destination should be enough. You don't need to have all this extra knowledge. And my estimate is that you should be more than okay with about 60% of the channels currently because we have a lot of redundancy in the channel structure itself.
How long is that? Is that like a minute? Is that like 20 minutes? Is that like 5 seconds?
That depends on the implementation and the gossip message, the gossip implementation you use. We have a couple of protocols or couple of mechanisms that we use. Initially, it was basically I connect to you, I dump my entire topology onto you. That hurt us quite a lot when we operated the Blockstream store because we had like 300 connections, and every time we would restart this node, it would take hours, if not days, to basically get through this whole dump of incoming messages, because every single message is also signed, and you need to go and check stuff on chain for it to be valid. So a lot of this information is exactly it's redundant. And some nodes might send us old information, and then we go check on-chain that this channel exists, and it doesn't exist anymore. And so we just did on-chain lookups that were basically useless, and we have to remember all of that stuff. So there's a lot of optimization potential in there.
Are there any like DDoS protections in terms of like if you tell me here's a channel, but like if this channel hasn't been existed for like I don't know 2 weeks or something, obviously it's like. And you made me like do all these calculations. Like I just like, hey, like there's no way that you didn't know that it hasn't been existing for like 2 weeks. So like this is like when you were.
We actually have nodes that lag months behind the current blockchain head. So it's really bad. Like 10% of our bug reports are actually due to people not having waited for their Bitcoin D to have to sync up. So we don't punish these currently. It would be nice to eventually have the information be part of the message itself. Basically, have a Merkle proof that this output exists in the latest UTXO set. But we are still not so sure about which form that would have, and we don't have UTXO commitments in the blockchain anyway. So that might eventually work, but currently isn't that nice. That being said, we are working on, especially Fabrice has been pushing hard on optimizing the protocols for gossip, because they are running on mobile phones, which do have certain power and computational constraints. So that's mostly been the async team that has pushed for a more clever and less dumb versions of the gossip protocol. So we now have, I think we now have a way for us to request ranges of channels from individual peers. So I can say, okay, give me anything of interest between block heights 500,000 to 510,000, and so you can sort of throttle how much information you get from individual peers. You can also split up this retrieval of information across multiple of your peers. So we're slowly getting there, and I think Bastien is working on or looking into Minisketch as well.
Yes.
And we'll let Fabrice tell us about how well that is working. But yes, this is currently our most CPU and power hungry thing out there, and it basically is just us gossiping about what channels exist and which nodes exist. Okay, so that's basically the entire stack we have. But since I annotated all of these titles with the bolts, you can look these things up. I think it's only fair that I also add the last few bolts that I haven't mentioned so far, and that would be the DNS Bootstrap protocol. Basically, it's a phone book for you to look up where individual nodes are. So if you don't know anybody in the network, you need a way to contact your first peer. And what this basically does is you have a domain name that you can look up on using DNS, and it will spit out a number of potential peers. since we need to have the node ID before we can actually start talking to them, we're actually using the SRV records to serve you the node ID first, and then you can look up the A or AAAA records for these domains, and then you know whom to contact. This also allows you to, if you have a channel that you wanted to have open initially, that you had at some point, you can reestablish connection with them without having to go through the gossip thing first, and you can just ask my server or roast beef server which nodes these are. This is just a side lookup basically. It's an optimization. You're not really trusting the DNS seeds at all because you're actually verifying that the identity you're talking to is who you were expecting to. And this, the final piece are the invoices that Rusty is really proud about. Oh, by the way, this is the same mechanism we also use for Bitcoin, and I operate DNS seeds for both of them. So it's really easy to operate them, and we just have a bunch of these that we can query. The invoices are sort of the party piece of this whole thing. Since for HLCs we need to exchange the payment hashes and the payment pre-images ahead of time, so we need to set them up. This is really came out of this need to have the recipient tell the sender what payment hash to use. And so the invoice basically includes a couple of pieces of data. One is the payment hash itself, but we also include a description and an amount of what to send in the minimal case. So that way you can actually check by just reading this. This is LNBC, so this is Lightning Network Bitcoin, 2500 U, which is the abbreviation for micro. Well, they didn't have a mu, so we used it. So this is 2.5 milli bitcoins, and the description we have is we can have this. We can have whatever is Unicode encodable, so emojis or whatever, and we have lots of more fields we can add here. We can add fallback addresses for on-chain payments. We can add hints about which channels are currently correctly balanced for us to receive this amount. So there's a whole lot of stuff we can add to this. The spec is quite extensive in what it allows us to do. Many people were annoyed that we went with this invoice sort of use case first. But we saw it as both a way to fix the exchange of the payment hash, as well as sort of covering like 90% of the use cases out there, which are usually, hey, I want to buy this, so give me an invoice and I'll pay it. One interesting side aspect of this invoice is that you can actually have a proof of payment for these as well. So if I go to Felix and Felix says, hey, you can have a cup of coffee if you pay me 200 millibitcoin, well, that's quite an expensive coffee. And I actually perform this payment, me having the invoice and then receiving the pre-image, which is him acknowledging receipt of this payment, basically is something that we could go to a judge and ask the judge to enforce. So I have both, this is the agreement, and I can have the proof that I paid this. And in combination, we can then go to an external party and say, hey, I did pay, he didn't give me my coffee. So that's that part. Yeah, so this is also BEC32 encoded, which is always a weird encoding, but it works awesomely well. Yeah. Oh, we also have timeouts, so yeah, just an interesting side note. And I think
timeouts regarded in like the HDLC timeout thing too. That, like, if there's a very short time there, and I can construct like an HJC path.
Yeah. So obviously, within 1 minute is not enforceable in Bitcoin at all, because our granularity is 10 minutes in the best case. So this is basically just a best effort thing, where we say, okay, I want to buy something from you, and you have a hot coffee basically sitting right next to you, and you say, okay, if you pay in the next 30 seconds because there's other guys waiting behind you, then you're good, and you will get your coffee. But if I can't manage to pay this in time, then you will just say, okay, go away. So this is not enforced really. It's a gentleman's agreement between the implementations that basically say, okay, I will accept the payment if it comes in time. If it comes after this 1 minute, then I will just reject it and fail it. And that basically then translates to being offered an HLC and then rejecting it right away because the timeout has expired, even though I could grab that payment with the pre-image that I have. But we thought it is just a nice usability feature for people to say, okay, I promise you that I won't accept this if it comes late, and the wallet that is sending will not even try to send it if the timeout has already expired. Yeah.
Is there actually defined behavior in the implementations, maybe if an invoice is paid twice?
So invoices being paid twice is dangerous. So the whole HLC construction is based on me being me receiving a pre-image to a payment hash that I don't know yet, right? So let's say through you I pay some coffee shop. And I extend an HLC telling you, hey, if you can give me a pre-image that matches A, then you will get your money. You don't have that initially, right? But I give you a hint that you might try and ask the coffee place. So the first time you turn around and ask the coffee place, hey, you can get this money if you can give me a pre-image matching A. And this payment goes through, and you will learn actually the pre-image to A, right? So now I try to pay this a second time, and I say, hey, you can get this money if you have a pre-image to A. Now you have that already. Will you turn around and ask the coffee shop again? Probably not, though all of the implementations currently will behave correctly. So this is a bit of we went towards a way of not being actively stealing people's money in favor of sort of encourage. We're trying to not encourage that, but we will allow it currently. So never use a payment pre-image twice. And since the payment pre-image is the payment hash is bound to an invoice, you shouldn't reuse an invoice multiple times. Yes.
So I have a question about the gossip part that you were talking about. You know, very naively from the RPC side, list channels, I get the channel twice, different fees. Like, is that redundancy reflected on the gossip level or not?
So we will treat. So you get the same channel multiple times?
Well, like different directions and different fee rates.
Oh yeah.
Right. That makes sense on the RPC side, I guess.
So we on the gossip side we treat a channel is announced using a channel announcement. And then for each direction, we have independent channel updates. So if you look at, for example, C-Lightning's API, it will always return each channel twice. If both channel updates have been received. If it shows you only one side of the channel, then the other channel update hasn't arrived. So we are really close to the gossip protocol itself. It might be confusing because you suddenly see twice as many channels, or many channels are duplicated, one for each direction. And so you should always collate them into a single channel and then differentiate between the directions. Yes. That's one thing that we went for, is basically that I as the outgoing side of a channel should be the guy who determines what constraints and policies are enforced there. And so these are two directions are handled completely independently from each other. And you could also not do channel updates at all for your side, so people will not route through you in that direction, but in the other direction. Not that useful, actually. So thank you so much, and thank you so much for the questions. I really enjoyed this. So let's keep at it.